In this video, we demonstrate ROADVIEW HD map positioning in Muonio, Lapland, Finland. On the left side, you can see the trajectory of the HD map data recording. On the right side, you can see a visualization of a semantic point cloud recorded from the same trajectory. To align the point cloud data, we used a graph-SLAM georeferencing method called Global LiDAR Odometry via smoothing and mapping, or GLOSAM. This method jointly optimizes semantic-aided LiDAR odometry and loop closure constraints together with satellite navigation positions. The aligned point cloud data was then used to build the HD map representation for vehicle positioning. The FGI Arvo vehicle, shown on the right and equipped with a Velodyne VLS-128 LiDAR sensor, was used to record the data for building the HD map for this demonstration. The VTT Martti vehicle, shown on the left and equipped with a Robustness 128 beam LiDAR sensor, was used to demonstrate the HD map positioning. Since the point cloud of the entire area contains too much data for real-time autonomous vehicle positioning, it must be processed before use. For this demonstration, the georeference point cloud was processed to represent the Muonio area as an EA-NDT HD map developed in ROADVIEW. The EA-NDT HD map represents the scene as three-dimensional normal distributions, which are used to position the current LiDAR sensor view within the map. The EA-NDT HD map uses semantic segmentation to filter out moving objects and vegetation from the data. By representing only the remaining static points in the EA-NDT HD map, the data size is reduced substantially. Here we visualize the Muonio area at different times from the front cameras of both vehicles to highlight the changes in the environment. The amount of snow significantly changes the surroundings, but there are also other differences, such as a missing guidepost, parked vehicles, and Christmas decorations on the light poles. The video pop-out on the left shows the FGI Arvo view at the end of winter in April 2025, during the data recording used to build the HD map. The video pop-out on the right shows the VTT Martti view 9 months later, in midwinter in January 2026, during the HD map positioning demonstration. The demonstration shows that HD map positioning performs surprisingly well despite of these changes in the environment. The HD map positioning demonstration drive starts from a parking lot with VTT Martti. The positioning system runs on an NVIDIA Jetson installed in the vehicle and is accessed via a laptop from the passenger seat. All computations are performed on board in real time. The video pop-out on the left shows the front camera view of Martti during the demonstration. The video pop-out on the right visualizes both the current and all previous HD map position estimates using axis symbols. This allows the full estimated trajectory to be observed as it is being generated. The current LiDAR scan is also visualized on top of the EA-NDT HD map. The LiDAR scan points are shown as smaller points, while the center of each EA-NDT HD map cell is shown as larger points. Each time a new 360-degree scan becomes available from the LiDAR sensor, the HD map ROS positioning node receives it. New LiDAR scans are processed at a frequency of 10 Hz, enabling continuous real-time positioning. First, the new scan is motion compensated based on the previous odometry estimate. Then, the motion compensated LiDAR scan is aligned with the map to obtain a refined position estimate. After that, the updated position becomes available, and the node waits for the next LiDAR scan to arrive. Although the current environment appears very different from when the map was built, the HD map positioning remains reliable. Observing the trajectory shows that the system provides a smooth position estimate, not only on straight segments but also in curved sections of the route. The winter conditions also create small bumps in the road, which cause minor vehicle vibrations visible in the video. However, these vibrations do not affect the positioning performance. Neither other road users nor the passing truck disturb the positioning. The HD map positioning is an alternative solution to satellite navigation. Its advantage is that once the map has been built, satellite navigation measurements are no longer required during operation. Only the map and the sensor data are required to position the vehicle, which makes it inherently independent of external radio signals. Therefore, HD map positioning can provide a reliable position estimate even when satellite signals are jammed, spoofed, or unavailable in obstructed areas such as near tall buildings, in forested areas, or inside tunnels. Another advantage over satellite navigation is that while satellite navigation typically provides only position, HD map positioning provides both position and orientation. Here the vehicle makes a U-turn on the E8 road, and the HD map positioning estimate remains reliable throughout the maneuver. During the U-turn, the vehicle undergoes continuous rotation and changing curvature, which makes accurate orientation estimation particularly important. The positioning estimate follows this change smoothly, without visible discontinuities or sudden jumps. After completing the turn, the HD map position estimate shows how the vehicle follows the same path back toward the Muonio main intersection. The new trajectory aligns closely with the previously driven path, demonstrating consistency in both position and orientation estimates. As the vehicle approaches the intersection, it turns right toward the parking lot where the demonstration began. Now the HD map position estimates from the beginning of the demonstration are visible on the right, and VTT Martti is approaching the previously driven trajectory again. Here the new position estimates begin to overlap with the beginning of the trajectory. It can be seen that the new trajectory closely matches the one from the start of the demonstration. The overlapping trajectories further illustrate the stability of the HD map positioning over the entire route.